Hello, everyone. Welcome back to Jump On Air. We're so happy you've chosen to spend some of your Wednesday with us as we explore statistics, science, data, and of course, Jump. My name is Julian Paris. I am the Learning Strategy Manager here at Jump Software. And as always, I get the great privilege to be your host for Jump On Air. And we have a really great show for you today, full of great speakers who are going to share their wisdom with us and share their stories with us. I'm going to be showing this schedule throughout the broadcast so that you know that we'll stay on time. And if you have to leave, you can always come back to catch your favorite segments. That one link to remember is jump.com/jumponair, which will always reconnect you right back to the live stream, no matter which device you're on. So take us on a run with you, take us up to the kitchen on your phone. Jump.com/jumponair is the one link to remember. After the show, we hope you'll visit us on our community, community.jump.com/jumponair. There you can watch the on-demand episodes from really any of our broadcasts. You can watch the individual segments if you have a favorite show, and you can interact with our guests and leave comments. We really hope you give us some suggestions for our upcoming Jump On Air broadcasts. So make sure to visit us at community.jump.com/jumponair. Now, I always like to start the show with a little bit of a segment, as you know, and today I'm doing a segment called Worst or Wise Graph Wednesday, where we decide, is a graph the worst or is it a wise graph? And to do this, I want to actually introduce you to a special graph that a great friend of mine sent me. And the introduction I got to it when she sent it to me was, everyone is roasting this figure, but I have to say I love it. So this is a great setup for a worst or wise. Let me show you the graph. And I'm going to zoom in here so you could take a look at it. And you don't have to worry about parsing it. We're actually going to spend a bit of time talking through what this is actually showing. But very briefly, this is showing deaths as an increase or decrease on the x-axis. And it's showing the average number of deaths per day. And it's plotting time as the connectivity of this line. So it is showing spirals for how these things are changing in terms of their average number, but also the rate of change. And my friend who sent this to me, as I pointed out, said that everyone is roasting this figure on Twitter. And I wanted to show you some of the excerpts of my favorite, comments of people roasting this, but they actually deleted the post when I went to go get that last night. So I can't even show you some of the hilarious comments people had. But I will share with you a couple of the things my friend said about this figure. And I should say, this friend of mine, this is probably one of the smartest people I know. So I think it pushed me to think about whether this graph is really good or bad. First, she said this is a doom tornado, and I thought that was pretty appropriate. But then added this, that come on, you know this chart has moxie. It's so bold, it transcends questions of chart noise. And I thought that was a great way of saying something, but it still made me question, is this graph the worst or is it wise? And so let's actually dig into this. I'm not going to use those data. I want to use something a little more neutral. So I pulled 50 years of average exchange rate data by country. And so what we have is many series, just like that graph did, of different countries. But we're looking at the exchange rate and how it changes over time. And that particular type of graph really requires some type of time. And so to start with these data, I'll just orient you. We're looking at exchange rate. And so for the first row here for United Kingdom, $1 back in 1971 in January would buy you 41 pence. And then we see the exchange rate over time for the different months. I've made a couple of columns we'll need to make that plot. I have a moving average and a difference. The moving average just takes a window of plus or minus 1 day. And the difference is just the difference from one row to the next row. Those are all functions you can do in Jump just by right-clicking. It's a new formula column row, and you'll see that you have options for moving average, you have options for smoothed versions of that, and difference. I also have a count in series. So this is just what value this is within the United Kingdom across time. And so that'll change to 0 for every other country. We'll use that in a minute. Before we do anything, let's just make a plot that we would normally make for a time series data like this. And I'm just going to apply a data filter where we're looking at just 1971 and just the United Kingdom so we don't make things too complicated at the start. And so I'm going to go into Graph Builder and let's just make our standard time series plot. And a way you might do that is take something like the date. Let's take our exchange rate and usually we'll put on a line. I'll actually keep the points on, and that's just 1971. The exchange rate went down a bit, so we got fewer pence for every dollar throughout the year of 1971. And we're all used to that graph, so reading that and parsing it was pretty easy for us. Okay, let's try to make that other graph. And just to remind you of what it looked like, we have an increase or decrease on the x-axis, so a difference, and we have the average in a particular window. And so that's our moving average column. Okay, so let's make this graph. And so we'll go back into Graph Builder. We're going to not use date. Date is implied by the connectivity of the line, so remember that. We're going to start just by putting the difference on the x. We're going to put the moving average on the y. We're going to click on the line and keep the points, but notice that the way JMP defaults to connecting this line is based on the x-axis, and that's reasonable in most graphs. But we need to connect based on time, and our data is ordered by time, so we can actually use this option under the control panel for row order for the line element. And that's the trick here, is that we're going to order the connectivity by time, or by the row occurrence in the data table. And to make things extra clear for ourselves, just so we can see it's doing that, I'm going to right-click on the count in series, and I'm going to use that as a marker. That is, I'm going to use the number that occurs in each of those rows as the marker here. And that'll be really useful later on as we actually try to see what this thing is doing. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we have our two graphs, and I'm actually going to pull open the graph comparison script I have here where I've already laid these out, because what I want to do is give this graph on the right a chance, because it's not familiar to us. So maybe it's non-familiarity is what makes it seem like the worst, but it's actually quite wise. So what we're going to do is look through the typical plot, and let's try to map it into a new cognitive space for ourselves. Okay, so across the year of 1971, we see that it's pretty flat in terms of the exchange rate. And if we look on the left, that's pretty obvious based on the flatness across the dimension of time here on the x. If we look on the right, that just means a clustering of the points there. They're not moving in any direction, and the average is staying the same. Okay. On the left, we have a drop in the exchange rate. So on the right, in order to show that drop, what we have is a deflection to the left. The differences are moving into the negative space, so the next row is lower than the row before it. And the moving average is going down because the rate is dropping. Okay, so we have a deflection to the left. Now, there's a little bump here, right, where the rate stabilized, and so that's a deflection back to 0 for a difference, but then it started dropping again, so we deflect back out to the left. And you'll notice I centered this at 0 because that's going to help us see, where that is. If we had it centered at the average of that, it wouldn't be as useful. So for that type of graph, make sure you center at 0. Okay, I'm not convinced. I honestly go with my intuition here and still think it's the worst. But let's give ourselves another chance. And to make this kind of a game, I'm going to hide this graph as I change to 1972. And let's see if we can think about what it's going to be like. So on the left, we have basically flat, right? So it's pretty good for the first few months. A sharp increase in the rate, so more pence per dollar, flat, and then an increase again. So in your head, can you plot what you think that's going to be on the left or on the right? And I'll actually just make this axis a little more reasonable. Well, that's not what I expected. I don't know if that's what you expected. I still don't read that graph well. But okay, let's try it again. 12, 13, 14, 15, that's relatively flat. Deflection to the right, back to flat, and deflection to the right, and then kind of levels off. Okay, let's just try one more. I'm still not convinced. 1973. This one should be easy, right? Down, then back up. Down, then back up. What are we going to get on the right? Well, that's just bizarre. I didn't expect that either. So far, I'm not that convinced. But remember, this plot is meant to show a lot of things at once. So let's actually just look at maybe multiple series here. I'm going to turn on 73, 74, 75, 76. And on the left, we're pretty good at keeping track of the dimension of time because it's a true dimension in the graph, left to right. And if we look at the graph on the right, unfortunately, all of that dimensionality gets lost because connectivity is a very poor thing to show based on connectivity. So that dimension just gets lost. So I'm going to put this online, that table. You can play with it yourself. But as far as I'm concerned, worst or wise, this is the worst graph. And so I'm sorry to my friend who thinks it has moxie. I just don't see it. So that's been your edition of Worst or Wise for this Graph Wednesday. We'll do some more of these if we have some time, but I hope that was informative for you. In our next segment, I'm actually pleased to show that we'll see some WISE graphs, and actually that's pretty appropriate because Scott Wise, Senior Manager of JMP Education, is here to do his featured program, Best of Pictures from the Gallery.
And My name is Scott Wise, and as Jillian said, we're here to show you some WISE graphs. For those that are new to pictures from the gallery, we go every year and we try to take 6 challenging graph views and show how they can be done in Graph Builder with some common tips and tricks. These are compelling graphs, and we're going to show you kind of the best of the past. So we've got 4 that we're going to queue up. These are going to be compelling graphs. We're going to include some words of wisdom, and we're going to include some relevant scientific data that will be of interest. So there's the 4 we're going to look at today. Let's dive right in. We're going to look at a positional chart, a marginal chart, a Gantt chart, and then Zan, I'll talk about Zan in a second, gave us a mystery chart we're supposed to figure out. All right, so let's start first with a positional chart. So the words from the WISE here: wonder is the heaviest element on the periodic table. Even a tiny fleck of it stops time. A poet wrote this. Now, why is this relevant? Well, this is, if you can guess, this is the periodic table, and it's been colored by ionization energy. And it's been showing up in the news because ionization energy is a way they're looking to kill and control the virus bacteria with things such as UV light and BPI air cleaners. So this is a positional chart, right? You see it, you know what this shape is. If you've been in any science class, you recognize the periodic table. To do it, we are going to take advantage of categorical X and Y, continuous color, but also there's a reverse order that's really important. And marker settings. So let's see how easy this is to work. You will be given this journal. In this journal, you will have access to all the data, the scripts to make the graph, and individual steps. So all that's available to you, but I will show you how to make it live here. All right, so here is my data. I can see my period, my group, and my elements. And I have my ionization energy. I'm going to open up the graph builder. I'm going to put group on the X and period on the Y. And I'm going to color by the ionization energy. Now, you know in JMP you can hover over points and have it pull back the information from your graph and from the rows in your column. And helium's down here. Hydrogen's down here. I think I got this thing reversed. How do I help this? I'm going to right click, go to axis settings, and just click on this reverse order. Now this is looking a little bit better. Now I might want to make some changes here to how I have my colors, how I have my settings. So I'm going to go under legend settings. I'm going to turn off the one for period. I don't need that one. I'm going to go under my hotspot again. This is the red triangle. We like to call it hotspots. I'm going to put the legend at the bottom. I'm going to right click on the gradient, and let's try a better color gradient, maybe like a yellow to red. I would like it to turn it horizontal. So it's giving me a little preview of what it's going to look like. Maybe a log scale is better, and maybe a log scale with 5 levels is better. Now I say okay. I'm going to say done, and I'm going to adjust this. Now you're saying, Scott, that surely doesn't look like what you had before. You had squares, and I can see more of the color. So all we have to do at this point is highlight all my little points here. Right click, go to rows, go to row marker, turn on the squares, right click again, go to the graph, and now go to marker size. And based on the size of your graph, I usually select another, and it's kind of trial and error, but I think 19 might be good here, and 19 is not bad. And now you can see how to generate this positional chart here of our periodic table. And by the way, the hotter the color, the more ionization energy, and they're really looking to disrupt hydrogen within the virus. So that's one thing they're really looking at right now. All right, fantastic. So that's a nice view. Let's take a look at the second most popular chart from our series. And this one is a marginal plot. Marginal, okay, so let's talk first about the data here. I love song quotes. I'm a failed amateur musician here. So Pink Floyd, breathe, breathe in the air, don't be afraid to care. Great song off Dark Side of the Moon, Breathe. What are they talking about? Well, we've got pollution data. And actually, now that we've shut down a lot of our polluting cars and activities around the world, pollution's actually going down in many cities. This was looking at US cities. It was looking at two things you care about primarily when looking at pollution indexes. You look at ozone and you look at the particulates in the air, or the PM10. So this chart is unique because I have a scatter plot against ozone and PM10, but I managed to find a way to put a box plot on top of PM10 and a box plot to the left for ozone. So it gives me a second graph to look. So these kind of plots can have different elements of graph types, but it's generally called a marginal plot. To do it, we are going to do something called a dummy variable. Dummy variable is a way to set this up in JMP with a categorical column that's going to allow us to trigger a second view. Again, you'll get this journal. You'll have the raw steps available to you. Let's go up and pull up the data and do it together live. So here I have my city, my population, I got ozone here, I got my PM10 numbers, and I have this dummy. It is a categorical variable. You can call it anything you want. You can put anything in here that you want. It just has to be the same. And I just put X's. So I'm going to go into my graph builder. I'm going to go into my graph builder and we are going to pull in the ozone on the Y. We're going to put the PM10 on the X. I'm going to turn off the smoother up here in my graph element. So I've got my scatter diagram. And we can go ahead and color by population. So far, so good. Now, how do I get that box plot in? There's really no way to do it except if you have a dummy variable. Watch what I can do. Right to the left of PM10, I put it. I can click in here and change it away from points and make that the box plot. Now, to size it, go to where the label is, where it says dummy. I'm just going to put my hand right over it. You know, your pointer turns into this little grabber icon. I'm going to go to the right until I see it gives me this little diagonal line. That's the way I can control the label width, but it also controls the graph width for this section. And that is really cool. I don't want to call my Y smart chart a dummy. So we'll click out of that. I can even go into the axis setting here just under this little section, and I can take that X out for the label. So we're going to do the same thing up top and see if we can get one going. That one was for ozone. This one would be for PM10. I'm going to go through the same process. Change it to a box plot. Oh, by the way, it doesn't know what to do with this little extra square up here. It wants to do a box plot. I'm just going to remove it so it's blank. You can do that as well. I'm going to clear out the dummy variable. I'm going to make it much smaller. And I'm going to go to my axis settings again and take care of that label. Okay, so now I'll say done. Okay, still doesn't look good. It actually really did some strange things to my legend here. So under that red hotspot, go into my legend settings. Let's go ahead and just clean that up a little bit by deselecting a few things. And as well, I can right click on these box plots in new in JMP 15, which I'm showing you. You have different box plot styles, and I kind of like the solid box plot when I've got colors going on. And now we have a very smart chart. And now I can look at something like St. Louis, which wasn't that interesting in terms of ozone. It was not an outlier for ozone, but it's an outlier for the PM10, for the particulates in the air. And I can see it corresponds to that outlier. I can talk about Los Angeles, which again is pretty high on ozone, was an outlier for ozone, but was probably still within the fence of my outlier box plot there, although it's kind of floating up to the wrong area. So here's an example of how you can do a marginal chart or plot for yourself. All right. So great, beautiful views. So our third most popular chart, and this is a fun one here. This is a Gantt chart. Did you know you could create Gantt charts in JMP? You didn't have to go out and buy separate project management software. Now the quote is going to all be about wine, because one of my favorite inventors has a great quote: wine is sunlight held together by water. And I am an avid home brewer and actually a commercial winemaker in the Philippines. So I'm spending a lot of my time making my own wine at home, and that's actually taking off now that we're all sheltering in place. And it's relatively easy to do. So I'm sharing with you the steps to make wine, in this case, blackberry wine, something that we have great blackberries here in Texas. So a Gantt chart here basically showing you step by step what's going on in your project and your process and your flow. And JMP can handle these, and we can make it look quite striking as well as quite useful. So I'm going to share with you how we do that. So again, you have all the steps involved on this journal that we will share with you. But I'm going to go ahead and show you what the data looks like. So I have tasks. I have a start and end date. And it's also helpful for coloring purposes to have some sort of status. I have, it's in process, I've completed it, that type of thing. I haven't started it. Now, row is the most important thing. You saw Julian with his Death Tornado there having to use a row order. This is going to be another place where having something which has the time sequence for your steps or the logical sequence of your steps will help us make the chart the way we want. So I just got this row 1 through 25 here. So I'm going to click on the graph builder. Pretty easy to set up. I'm going to take my task. I'm going to put it on my Y. I am going to take my start and end date. I'm going to put it on my X. I am going to turn on bars and points that we are doing. In fact, I'll do them in that order. Points first and then the bars. Now you're saying that doesn't look so interesting. Instead of side by side, let's change the bar style to range. And now that's starting to flesh out a little better. Let's color it by the status. Okay. But it's all way out of order. It's trying to do some alphabetical stuff. I don't know what it's doing. What are you doing, JMP? So take your row, put it into frequency, then right click and order by the row descending. Now it is in order. Oh, and this is beautiful. Now, how do I clean up the view a little bit more? What we're going to do is we're going to go where it says start date and end date. And I'm going to change the marker to these little diamonds. And the reason is I like when you mix a diamond marker with a bar, you get kind of a chevron view. And that's a really nice way of looking at it. Now we can clean up our axis again, right click over here and go into the legend settings and just leave some semblance here of what the bar color is. I think that'll suffice. Now, under my axis settings, I can go in here and turn on some grid lines, and I could control kind of how many days I'm looking for as well, maybe as well. Given this is time, this is a great thing in JMP. Maybe I want to look at it every 5 days. And that will be how I get vertical lines. And now over here on the task, I'm going to go into the axis setting. Now this is a categorical column, so I can only really put some indicator lines next to the grid. And that helps, but it's not really easy to look and say, what's this red line? I can step 8, but it's not really visually standing out to me to be able to quickly look on this chart and see what belongs to what. And Julian, our host, showed me a great way of doing this. So if I go in and I go back to my axis setting, take advantage of putting in shaded ranges, kind of like we would if you bought special, college rolled paper, which had some contrasting lines. So I'm going to hit range. My step values are all whole numbers, so maybe between 0.5 and 1.5. I'm going to put a gray line, and it's already on a transparency of only 25%, and you can see what it adds down here in your preview box. And so you go and you can set the next one up maybe at 2.5 and 3.5. And I'm sure there's a great way to script all this if you're going to do this a lot, or save this as a option to always run your chart through. But this is just a fantastic way of getting that view. And now when I go and I highlight just on that part of my process, now the time shows up, now the shading shows up. All right, so that was the Gantt chart, and hopefully that will inspire you to do something creative with food or beverage as well in your time off. All right, are you ready for the mystery chart? So we're going to finish off with the mystery chart. Zan Gregg, who's our director of R&D for visualization and the creator of the graph builder, and he and his team have made these great views. He wanted our help. He says, I'm testing out a new chart. Can we do this in Graph Builder now with some tips and tricks? And would this be worth making a standard chart? Can you guess what this chart is? I'll give you a hint. It's not a trend chart. It's showing something over time, kind of like what Julian was showing, but it's doing it with blocks. It's doing it with segments. It looks like if it's gray and blue, it's going up a little bit. If it's red, it's going down. This is a Standard & Poor's stock. Okay, let me tell you about the data. I did this in particular because I was wanting to feel better about my stock. So the chairman of the board, Frank Sinatra, always said, that's life. You're riding high in April, shot down in May, but I'm going to change my tune when I'm back on top in June. And we pray that we can all be back on top in June, and we will be. Because as you can see, no matter how bad things have been in the past, we have rebounded. And this is a good way of making you feel better. So that's the data we're looking at. But this chart is a waterfall chart. So this is a popular chart in financial circles, but it's probably, I see it having a lot of scientific and engineering value as well. So let me show you how we're going to make a waterfall chart. So here's my Standard & Poor's data since 1928 by year. I did put in what decade it was from, but here's the average closing price, just kind of as an average thing we could use. And what we were doing was we were looking over a prior column, and we just set up a simple formula to do this. So basically it's the lag. We lag by a year. And then what that change was. So before it started in 1928, there was nothing to compare it to. So it's a big change, right? It went up 19.94. But the prior year it was 19.4, and then it went to 26.19. And of course, that is a $6.25% increase. You can see that it actually went down in 1930 when the Great Depression happened, and that was on average a $5.19 decrease. So we've got this information. What we'll do, we'll go to Graph Builder. On Graph Builder, we will go and we will put the year on the bottom. We will put the average close price and the prior directly in your y-axis. I'm going to ask for bars. I'm going to say bar range. Here's another place we're going to use the range. Now let's give me the view I want. I can take that continuous change category. I can put it on the color. It looks like it's doing what I want it to do, but not exactly. I think I got the colors reversed. So again, I'm going to right click on gradient, reverse the colors. And now it's back to where I want it. This is looking at everybody. So I do know that a popular thing to do is just take a look at the log instead of a linear. Sometimes it's better if we graph over the log. So I'm going to do the log. I'm going to turn on the grid lines here. We'll call this average price. And I'll remind myself it's the log. And now, down here on the year, under axis setting, I will turn on a few grid lines as well. And now I have a good way of showing everything you would want to see about the whole history of the Standard & Poor. And if you want to dive into this, setting up a local data filter to just look at, let's just take a look at the 80s or maybe the 70s, so we can get the oil crisis of the 70s in here. And now I can take a look at what the behavior has been so far. And this again is a waterfall chart. So pretty cool. So if you like this chart and you want to see more of this as a standard option within Graph, just beyond using these tips and tricks, please go out to the community and go out to the JMP wish list and put into the JMP wish list what you would like to see. Could be a graph view, you could want a diff tornado, you could want now this waterfall chart, you could want a different type of graph, you could want a different type of analytical method. So please, that we do listen to your input, and we do use that when making new releases of JMP. As well, in your journal, I'm going to leave you behind with a whole bunch of places to learn more. There's the full gallery on the community, so you can see all 30 views we have over the years. You can see some cool blogs, you can see some great videos, and you can see some good tutorial / self-help white paper material that will help you learn to graph, to report, to dashboard, and even to share on places like JMP Live and JMP Public more. And I think that's all the time we're going to have today. If there's any time, I can take any Q&A if any comes up, Julian. But otherwise,
yeah, I'll keep an eye on that for now. While we're waiting for people to put one in, why don't you show what that Pictures from the Gallery series on the community looks like, your full gallery link. And if people don't have their Q&A panel open, go ahead and open your Q&A panel. And if you have any questions for Scott, you can put them in there.
So Pictures from the Gallery takes you to where the full galleries are positioned. And there's quite a bit out here. And for example, this is Pictures from the Gallery 4. And you can go out and you can get the journal. You can go out and see just what you want to see. And if you do come and I will put a pitch in for our next discovery, there's a good possibility you might be able to see some more pictures from the gallery at our next discovery, because there are great graphs, and we like to have good wise graphs, as Julian says, smart graphs, compelling graphs, and showing detailed data in an easy and compelling way is the best way to make decisions, especially to influence others to make the right decision.
Outstanding. Well, thanks for showing that, Scott. And you're right. Yeah, we really do want wise graphs, and you certainly showed us a number of them today. So I'll grab back control, but we really appreciate you coming on JMP On Air to show us all of that. And I can't wait to see what more you have in store for us at Discovery.
Thank you.
Fantastic. Thanks, Scott. Our next speaker, we have Ross Methuselah back in another edition of Help, where he takes us through different aspects of the JMP Help.
Hi, everybody, and welcome to another edition of Help, a review of JMP's help resources and how to use them effectively. There we go. Wanted to make sure everybody caught the cute cat today. Needs some help. Anyway, I'm Ross Methuselah, and we're going to look today at one of the best help resources of all, which is your fellow JMP users who you can connect with for help through the JMP user community. So let's see how to go about that exactly. So down here, we're at the community homepage at community.jmp.com. This is the place to get help from your fellow JMP users or sometimes JMP staff with any unique or specialized problems that you might have that aren't covered in the JMP documentation or other help resources. Now, if you're not a member yet, just go to community.jmp.com and you can find a link to sign up. Community members provide help to one another, mainly through the discussion board. And we have a lot of discussions already up there. If you take a look right here, you can see we have nearly 220,000 discussions and counting. So if you have a specific question that you want to pose to the community, there's a decent chance that the question's already been asked and answered before. So it's a good idea before ever posting a question to head on over to the discussion board and have a quick search to see if your answer is already there. So I'm going to just do a quick search for something I was talking with one of our users about the other day. They were looking to combine separate date and time columns that they had into a single unified date and time column. So I've typed in my search query here. You can see I actually already get some hits right off the bat. But to pull up the full search results, you can hit enter or click the little spyglass icon. And I did that because I want to point out something to you in the list of results that you get when you search the community. You were probably noticing some of these green checkmark icons right here next to some of the posts. These green checkmarks indicate when a post has an accepted solution. So that is a reply that the original poster has tagged as having solved their problem. So if you're looking for posts that have verified answers, have a look for the little green checkmark. So I'm going to click on this first hit that we have here just to see what this looks like when we're looking at a post with a verified solution. At the top, you can see the question itself, and then right beneath it, you're going to find the accepted solution highlighted in this green box here that's labeled solution. So here we actually have a pretty nice solution with plenty of detail and screenshots provided by one of the JMP user community super users. So this is great. We have, thousands upon thousands upon thousands of questions that have already received verified answers. So definitely do a quick search when you have a question to see if you can find a verified answer that meets your needs. But sometimes that's not going to be the case, and you're going to need to make a post anew. So let's see just a few tips for how to do that. I'm going to go back to the main page for the discussion board. And in the top right corner here, I'm going to click Start a Discussion, this orange button. This is going to take you to a pretty standard discussion board screen where you have a place to type in a subject for your post and then also the body. The body of your post can contain text, images or screenshots, web links. You can also attach data tables, pretty much anything you need to get your question across as clearly as you can. And that's really the most important part about posting to the community is clarity. Over here on the right where it says stop and check, you can actually see we provide just a quick checklist for you to remind yourself what the primary components of a clear post are before posting your question. So let's just review briefly kind of what you would want to include to make sure that your post is nice and clear. First, you want a clear question or goal as your subject. You can see actually when I start typing in the subject, it's doing a quick search to maybe help you notice whether somebody has actually already asked your question before. And just having this clear subject is really important to help people when they're actually browsing the discussion board, sometimes looking to provide help to people to quickly determine whether they can actually provide the help that you need. And also later on, it helps other people, if they're searching for answers to questions, determine whether your post might be the same question as one that they have. Now down below in the body, you want to provide simple, clear context to make it exactly clear what help you need, what solution you're looking for. So you'd provide things like the specific solution that you're after. You might provide what you've tried already and what happened. So this would include any error messages you've received. Make sure to copy those in full. And some additional supporting materials are always good. You could put a screenshot in there, attach a example data table or other data file, which you can always do right here with the tool to upload. And then finally, any JSL code you're working with, definitely make sure to include that. When you do, use this little blue button here that says Insert JSL Script. This will bring up the JSL Syntax Highlighter, so you can type your code in here. And when you insert it, you can see that it's actually formatted specially. It's set off in this box, uses a monospace font. There'll be some syntax highlighting and so forth. And this is really helpful to make sure that your code is readable, and also to help the kind of engine under the hood of the community recognize when it's dealing with plain text versus code. So once we have our post ready to go, it's simple as just clicking the orange post button and then just waiting for the responses to start rolling in. Now, I'm not going to post this. I'll just click cancel for now. But the responses, once you post, should start coming in pretty fast here. I actually had a look at some user community data yesterday, and looking at posts from just the past 90 days, over 90% of posts received a reply within just 24 hours of being posted, and over 78% had an accepted solution within 24 hours. So if you have a specific question that isn't addressed in other places, post it to the community, and you're likely to get help pretty fast. So let's just review the basics again for how to seek help effectively on the community. First, remember that it's for specialized questions that aren't addressed in the JMP documentation, so always make sure to check the documentation first. Before posting anything to the community, go ahead and search the existing discussions just to see if your question's already been answered before. If it hasn't, make your post in a clear and succinct manner with plenty of supporting detail like screenshots, example data, or JSL code. Then when somebody replies to you with a real solution, make sure to mark it as an accepted solution so others can find it. And of course, maybe thank the person who helped you out too. If you'd like to learn more about the user community and how it can help you get the most out of JMP, join JMP On Air in 2 days, this Friday, May 8th, when a few JMP user community super users are going to join JMP Customer Care Manager Jeff Perkinson for another segment on the user community. Again, that's on JMP On Air this Friday, May 8th. Thanks, everybody. Julian, back to you.
Thanks so much, Ross. And yeah, great tips on using the community. We really invite anyone who hasn't seen it before, get out to community.jmp.com and see what resources are out there. In our next segment, we have Tom Donnelly here with us as Dr. DOE to talk about how we can stop using classical response service methodologies and whether we can do it cold turkey.
Well, thank you, Julian. As you can see from the title here, I tried to make it somewhat provocative or campy. So can you stop using classic response surface method designs cold turkey, or take too high optimal and call me in the morning? I hoped that that was a better title or more attractive than just how do I use the compare design platform in JMP. But that's really what we're going to be doing for the next 20 minutes. So I'm going to give some background. I've been doing DOE for a while, and I'm going to talk about classic response surface methodology. Then I'm going to do 2 examples. I'm going to first look at the results for 4-factor designs and again compare classic designs like Boxplot and Central Composite to optimal designs like the iOptimal design created by the custom design platform. We'll do it for 4 and 7 factors, and then we'll go out and we'll use the platform. The amount of time it takes to actually do everything is very quick and easy. And so I've captured a lot of this, the story in the slides to start with. And if there's time, we can even do some compare screening designs augmented to response surface. So I started using classic designs back in 1984, and this was before I even knew of any dedicated software for doing DOE. And I was strongly influenced by the DuPont Strategy of Experimentation course, which led me to getting the Classic Statistics for Experimenters by Boxhunter. And I was doing fractional factorials and Boxplankins and central composite designs, and pretty much doing all the calculations in spreadsheet software. And I was working for Honeywell at the time, and things were working out pretty well. Well, then I learned about the first DOE software company, and I joined that in 1987. And it was sort of a culture shock because the primary tool in that platform was using optimal designs, actually de-optimal designs. And again, the main reason for using optimal designs is to make your designs fit real world problems. I did that for about 20 years, taught a lot of courses around those methods, and occasionally had to use classic designs because people wanted to use them, but still was more of an optimal design person. Then I worked for the Army for about 4 years. That's why I'm on the JMP Defense and Aerospace team, still supporting the DoD and NASA. And that's where I began using JMP. And JMP has eye-optimal designs. If you all know Brad Jones, he's the inventor of that platform in JMP. And I joined SAS in 2008, and I've been working on DOE with customers ever since. So here are the takeaways from today. Again, if you're using design of experiments, the vast majority of the time you're going to use the custom DOE platform because that handles real world issues. That's where you can make your design fit the problem. If you've got continuous and categorical and blocking and mixture and hard to change factors, all of these things make it so that you often can't use a design out of a textbook. And so most of the time, I think that's where people are going to go, but occasionally you have an all continuous variable problem. And so there are good reasons to consider using classic designs. And in particular, I like to encourage people to look at as many factors as they can when they start. Usually we're going to be doing screening, but one of the problems I always ran into, particularly when I was helping customers doing DOE or when I was working for the Army, is people would often think the problem down to 3 or 4 factors because that's what the picture in the book shows. That's what the hand calculations were easy to do. And they often close the door to looking at more and more interactions with larger problems. So it's not that I'm advocating that we should all be doing really big designs, but I think we should be looking at how can we get the most number of factors into those designs. And so one of the interesting things you'll find about the custom DOE platform is that actually with 3 and 5 factors, the custom designer will actually give you a central composite design when it gives you an eye optimal, okay? And typically for 3 and 5 factors, you're gonna be doing about the same amount of work, but there's real opportunities, particularly at 4, 6, 7, and 8 factors, where you can do a lot less work than if you use the classic central composite and Box-Benken. And what I'm hoping to show today is why you should feel comfortable doing that by looking at the Compare Design platform. So the Compare Design platform is going to show us how these smaller eye-optimal designs can have strong power across all terms, as well as lower fraction of design space curves, basically saying lower predicted variance than the classic Box-Benken and central composites. So we'll see this slide at the end again, but that's essentially the message for today. So classic DOE in a nutshell, I think if you've ever taken a DOE course, you've probably seen cubes. Usually that you start with the 2-level examples with factorials and fractional factorials, but then you often move to 3-level. You'll see drawings like this, and the shaded points are the points we're going to actually use in a design. And if you take block 1, it's the half fraction. The mirror image of it is block 2. And if you put those two together, you get a full factorial. And then if you add the star points, the last cube on the right, where all the points are in the middle of the faces, you put that all together, that's actually a central composite in a cube design. And each of these designs could individually support a main effects model, which is the plane showing on the lower left. You need the first 2 blocks to support an interaction model, that's the case in the middle. And to really get curvature into your surface, you need to have all 3 of these. So you need more information to get a more complex model. And so these are the polynomials that support those curves. And I'm showing you the 3-factor examples. And here I'm showing those same models, but I'm making the point that as you go up in the number of factors, the big explosion in model is from the interactions. And so that's going up as k times k minus 1 over 2, whereas the main effects and squared effects just go up as k. And one of the things that I found that people with a more of a traditional focus, they'll look at doing the main effects, and then they'll say, well, now let's look at the interactions, and then let's go look at the curvature. The point is the curvature terms are second order as well, and they're not that much more than the interaction. So I highly recommend, if you do a screening design, you go right to response surface with the quadratics. And the other thing to keep in mind is if you don't put the squared terms in your model, then when you do optimization, your only optimum can be a corner. There's no way for it to be somewhere in the middle of the design space. So that's a really quick review of classic DOE. Here I want to compare the size of designs to the model that we're looking to support. So if we're looking to support a quadratic response surface model, the red circles show the actual number of terms in the model. And that's actually equal to the minimum design that you would get out of JMP. You'd have no degrees of freedom for model error, but you could at least fit the model. The green pluses show the default custom design from JMP, where we've added in 6 degrees of freedom for model error. So it goes up monotonically in parallel to the terms in the model. When we look at the size of the designs for the box banking and central composite, you see they kind of jump around. And that's because they're built from symmetry. It's we're going to have a graph in a minute or two showing some of these designs, and so we'll be able to see where that symmetry comes from. And you'll notice that at around 3 and 5, you're doing the same amount of work, particularly for the central composite, as you would with an I-optimal. Those are the 2 places where they coincide. But you'll notice there's an opportunity at 4 factors to do less work with the default I-optimal in JMP. And when you get to 6, 7, and 8 factors, you can see it's dramatically less. And so historically, I don't see people running large designs, and it's not, again, not that I'm encouraging people to go out and look for 70 run designs to do, but if you thought you could get there in 30 or 40 runs, maybe you would consider that. So we're going to look at a 4-factor case today. We're going to look at the 7-factor case today. And if time, we could even talk about how you could sort of get to the green line or a little bit above it in 2 steps. Where if you did a screening design, particularly a definitive screening design, here I'm saying if I had 11 factors in a 25 trial definitive screening design, I did the analysis, it's kind of ambiguous. You know, 3 of the factors look really important, but 3 are on the edge. What I could do is just add 12 more trials by augmenting, and I would get up to a 37 trial design, which is just a little bit bigger than the, if I knew what the right 6 factors were and went right for quadratic. So here's the shape of these classic designs. On the left is the box banking. People often describe this as you put a point in the middle of all the edges of a cube. So you're really missing the 8 corners of the cube. In the center, we've got where if you superimpose those 3 cubes from before, I've got all 8 corners, the center of all 6 faces, and 1 in the middle. And as I mentioned, if you did an I-optimal design with 3 factors, you'd get exactly the same thing. And if you did it with 5 factors, you'd get the same thing, only it would be a 5-dimensional cube. So the compare design platform has about 7 different types of output. I'm going to focus on the graphical ones, and it allows you to look at up to 5 designs at a time. So power analysis, prediction variance, fraction of design space, and correlations. And this is just the dialog box. I'll show you how we populate it in order to make the designs. But this is the comparison output of the power for the 5 designs that I've chosen. I've taken these 27 trial box banking, central composite, and I-optimal, which are the 4-factor designs that I created. And I gave them all the same number of center points, so I was trying to make them as apples and apples as I could to compare them. And then I made a 24 and a 21 trial design so that we could see, well, could I get a good design with less trials? And so here, if we look at the powers, a lot of people, this is something we look at, so we want to not miss an important variable. And usually in the DoD, they want powers of about 0.8, certainly for main effects and interactions. And if you look, you'll see that the central composite does really well on main effects and interactions, but it does the poorest for quadratics. Conversely, the box banking, which has got all those middles in its design, does the best on the quadratics, but is the weakest on the interactions and the main effects. And then we can look at this as we get smaller and smaller in the I-optimal, you'll see that the 27 trial, so the same size design, is a very strong second for all. And actually the 24 is also very strong. And I remind people that factor sparsity will help the power situation. And so here, if I have the full model on the left, and it turned out some of these terms weren't important, and I dropped them, I've dropped about half, and I'm left with the group in the right-hand side, you can see that the powers have all risen for those terms. So almost always your power will go up as you begin to do analysis and drop terms from the model because not everybody's going to be important. Some more output from JMP. Here you can see that we can look at the prediction variance profile. So this is the prediction profiler. I've stacked the 5 designs I've talked about for the 4 factors. And on the left, I show we're at the midpoint settings of everything. And on the right, I've kind of skewed things to off-center. And it's no surprise that the bottom graphs are very parabolic there because these are those box Benkens where I don't have data at the corners. But what you should see is that the lowest on the right, the lowest predicted variance at that off-center location is the 27 trial I-optimal, and even the 24 trial I-optimal is the second lowest. So it performs very well there. The fraction design space plot, something invented by Christine Anderson Cook. Here we show it for the prediction variance versus that fraction of the space for these 5 designs. And when you use the crosshair tool in JMP, which I have purposely put at 0.8 and 0.363 for the prediction variance, you get kind of a zoomed in view to see what's going on. The way you can think about this is we have that dotted line at the 50% mark. And so what we're saying is, you know, how good are these designs at predicting over about half of the design space? And you can see clearly the winner here is the 27 trial I-optimal, but finishing second is that 24 trial I-optimal. And it's not until we get to the 27 trial central composite that it finishes third. So even the 24 here is beginning to look like we could get a savings in running that design. Now, when it comes to the correlation, you're going to find that the classic designs here, at least on main effects and interactions, because they're orthogonal, it's completely white in this upper right-hand region. So up in this zone here, you'll see there's absolutely no correlation. However, there's pretty healthy correlation among the squared terms up in this region. Okay, that's going to be less so for the box Benken. Down here are the 3 I-optimals, and you'll notice there's a light gray shading on some of the pairs here by which there is slight correlations, but they're running about 0.10. And so if you look at the average values for all of these, you'll see that the I-optimal designs still perform very well, and there's no complete confoundings anywhere. And this graph is not something right out of the Compare Design platform. It's something I put together where I tallied up all of the low, middle, and high settings for each of these designs. And I think it helps to tell the story here as to why the box Benken doesn't perform well for the main effects and interactions. You can see it's dominated by the large number of mid-levels here. It's also interesting to see that it just turned out that this design has got the same number of mid-levels as it's got lows and highs. And that actually turned out to be the case for the 24 trial I-optimal. When we go to the larger numbers of factors, we're going to see that that's not going to hold up. But here's the I-optimals, and you can see why they're still comparable in terms of the total number of lows, middles, and highs. So let's look at the 7-factor case. And here's that same counts of the levels of occurrences. And here I even decided to divide by the number of factors. So you get kind of the average number at each level. And here you can see that that central composite, even though we've got 80 runs total, we're only getting 14 mid-levels per factor. Okay, but the box Benken is getting 38. And so you can see that this one's sort of overly biased toward getting the curvature effects, but not getting the main effects and interactions. And this is the opposite. Whereas all of the I-optimal designs, and I've got them going from 42 to 46 to 50, those are the 3 we're actually going to use in the Compare Design platform. The 62 run case, so that's the same size as the box Benken, and the 80 run case, which is the same size as central composite, they're kind of overkill. So I didn't actually include them because you can only do up to 5 designs. But this gives you some feeling as you head into this what we're going to see. Now, this graph with that many terms in it, it's going to be very hard to read. So what I did was cut out the X2 interaction through the X6 squared term, because you can still see the story here. With this many trials, everybody's power is well above 0.9 for the main effects and well above that for the interaction effects. I should say not everybody, the Box-Benken is not quite up there. And then if we look at the curvature effects, here you can see the Box-Benken effect. The one that's really low is that central composite. Remember, there were only 14 per factor. And you can see the fall off from 50 to 46 to 42 for the 3i optimal design. So once again, the story down below, the Box-Benken, great for quadratics, not so good for interactions. Central composite, great for main effects and interactions, but in this case, quite poor for quadratics. And the I-optimal designs were strong second and strong third for all. So again, a good compromise. The same story is true with the prediction profile. The lowest and second lowest are going to be the 50 trial and the 46 trial I-optimal. And if we look at the fraction design space plot again, we can see that the lowest is the 50 trial I-optimal, second lowest is the 46 before the 80 trial Box-Benken starts to get close to it. And if you're wondering about those two designs I left out, I added them back in. This is what I meant by overkill. For the same amount of work as the classic designs, they were substantially better at their prediction variance. And do we need to take those extra trials? I would argue that we don't. And again, the correlation of the model terms here, again, you get, this is the one area where I would say the classic designs, you can make the case that they are completely orthogonal here, but you can see that the degree of correlation is quite low across the I-optimal designs. So let's now go do this. And so I have a couple of tips for using the compare design platform. The first thing is you want to open the files in the order you want the design to appear in the chart legends. And then when we open the reference file, open that design first, make it the active data table. Then we launch the DOE platform, we go to the design diagnostics item, and then we pick the compare design platform item. When we go to highlight the designs to make it, we're going to shift click to select them. And if the names are identical, we would use the match columns, but we're going to see that we won't need to do that. So let me put this out of the way, and here's my jump home window. Here are the I just dragged one of my designs away. Oh, I opened it. Let's see, now this is already going to sort of screw things up because I've opened up the 27 first. So I'm going to close it. And what I want to open first is my 21. Now I'm going to have to do them all at one at a time. So there's the 21. Here's the 24. The 27. And then the central composite and the Box-Benken. Okay, and so now what I'm going to do is make the active data table this 21 trial design, go to the DOE platform, design diagnostics, compare designs, bring that dialog box over. And now you can see, I'll make it kind of tall. I can add to this list, I want to also compare the 24, the 27, the I-optimal, the central composite, and the Box-Benken. And so now that I've selected them all, there is a match column option just in case the factor names weren't identical. For example, what if someone gave you a design and they said temperature all spelled out, you had made a design and you had temp, abbreviated, you could tell JMP, hey, those two things are really the same things. But we shouldn't need to do that here because they're all the same. We click OK. And that brings us to our compare design platform. The default model is that quadratic model, but you could edit it. Okay, so that's in here. And as we go down, we have the tables of numbers for the power analysis, and all of this is relative to the 4-factor 21 unique trial design. But here's that power graph that I showed you. Again, I've I had taken the time to kind of clean this up a little bit, but it tells the exact same story. Box banking, great for quadratic. Central composite, great for main effects and interactions. But the optimal design's good compromises. And even with 24 trials, we have a strong power across all the factors. Here's the prediction variance where I changed, the settings to go off axis. Here's that fraction design space plot. I kind of zoomed it to about 1 so we could get a little more detail. And if you want to zoom in here, you get your crosshair tool, and then you can click and you'll get that magnifier showing you where, kind of a real zoom in on reading the values in a graph. And then down below, we have some more of the more numerical tabular output. So that's making it through at least once. And I think that takes me close to the end of time here. So let me ask Julian if there's any questions. And if there are, I'd be happy to take them. But otherwise, here are those same takeaways that I listed at the beginning. And if you're ready to take back control, Julian, I'm happy to give it.
Fantastic, Tom. Yeah, we'll keep the questions for the community because we're out of time, but that was really great. I think a lot of our viewers will love to try compare designs for themselves too. So again, if anyone does have questions, please visit us at community.jump.com/jumponair. Tom will take a look at his segment page, and if you have questions, I'm sure he'd love to field them. Thanks so much again, Tom.
Thank you.
In our next segment, we have Ryan DeWitt back for another edition of Have You Tried, where he's going to talk us through creating Pareto plots in JMP.
Pareto charts or Pareto plots are basically a ranked order histogram that will most likely include a cumulative percentage line. I'll demo this in JMP using the failure sample dataset. Pareto plots are extremely useful for analyzing what problems need attention first, because the taller bars on the chart, which represent frequency, clearly illustrate which variables have the greatest cumulative effect on a given system. The Pareto plot provides a visualization of the Pareto principle, a theory maintaining that 80% of the output in a given situation or system is produced by 20% of the input. With the failure sample data opened in JMP, let's select from Analyze, Quality and Process, then Pareto Plot. Select Failure and click Y, Cause, or drag it over. This column lists the causes of the failure and is the variable that you want to inspect. Select N and click Frequency or drag that over. This column lists the number of times each type of defect occurred. Click OK. The left axis represents the count of failures, and the right axis represents the percentage of failures in each category. The bars are in decreasing order with the most frequently occurring failure to the left. The curve indicates the cumulative failures from left to right. Now select Label Cumulative Percent Points from the red triangle menu next to the Pareto plot. Note that contamination accounts for approximately 45% of the failures, and if we include oxide defect with miscellaneous, these account for the 80% of failures. Use the failure sample data and explore the additional red triangle settings, such as threshold of combined causes. Thanks for using JMP.
Thanks so much, Ryan. That was really informative, and I know a lot of our users use Pareto plots, so that's a great demonstration of how to get them easily in JMP. In our next segment, we have Fiona Kelly here to take us through the methodology of science.
Hi, everyone. I'm Fiona Kelly. I'm going to go over the methodology of science here. I am one of the Salesforce developers here at JMP. And I quite love logic and communication. And so we're going to get a little abstract today. We're going to get a little bit out of JMP, and we're going to talk about how we get to the point of having the data points that we get in JMP. So what is this all about? Understanding our thoughts helps us to refine and clarify them. So understanding how it is we think, the process that gets us to what we think and what we're saying, actually helps us refine our message, both internally and to others. We can expand our understanding by understanding how we understand something. Say that one 10 times fast. Understanding our processes is pivotal to providing the guidance for others to understand our process too. So anytime we need someone else to understand what we're saying, we need to be able to present our process to them. And in order to do that, we need to understand the process we went through ourselves. So a couple topics. We're not really going to use these words today. We're going to keep things kind of light, but these are really kind of the 4 major areas we're going to cover today. Phenomenology, which is the study of our existence, the unique existence of a person in the world from the person's perspective. Developmental psychology is the study of how a person learns. It's the study of understanding. Epistemology is the study of what it means to know something. And logic is really just the process. So how does this connect? Phenomenology is the action of learning. That's actually how we learn. Developmental psychology is the process of learning. Epistemology is the knowing bit. And logic is the pathway. Logic is how it all works. So we're going to spend extra time today on logic because refining that is going to refine all of the other 3. But first, let's start with a little bit of developmental psychology. Dr. Jean Piaget was a psychologist, a Swiss psychologist, who began as a zoologist and developed into an epistemologist, so studying understanding. And he began working with children and developing products for children to learn how to read. He developed, after a time, an understanding through research. There were really 4 stages to understanding. There was the sensory motor stage, and this is where I touch or interact with something, and I feel or I sense some kind of a reaction. Something's happening, I am existing. The pre-operational stage is when I begin interacting with classes of things. So you notice we've got different toys down here at the bottom, and the things I'm going to do with these toys will change. At the concrete operational, we're beginning to get a little bit more abstract. At this point, I'm beginning to understand things like classes and colors, and that these things can be differentiated, not just because of how I interact with them, but because there's properties, sort of abstract, not really there, living in our head ideas. And at formal operations, we're putting all of this together. Now we can say, not only do I know how something will work, not only do I classify it in a certain way, but I can predict what might happen if I did something else. Putting it together. So I love the term scaffolding. Scaffolding is just so wonderful in logic because it's really a step-by-step process. Just like a painter's scaffold, I start at the bottom where I experience and I gain some information. Then I identify some things about that experience. I begin developing rules about those things. Every time I experience this property, I can do these things. So now I have some rules about what these properties are in terms of interaction, their colors, their feelings, their sounds. And last but not least, I can begin predicting. I can start saying, okay, if this comes up again, even in a new situation, I can probably figure out where it's going to go from there. This is, in fact, Piaget's step 1, 2, 3, and 4. And it is the upward scaffolding of learning. Okay, Legos. Everybody knows Legos. So I'm walking in my living room, and I step on a Lego. It hurts a lot. What am I learning from this? There's an experience. There's sensation. There is realization of what's going on. Okay, what hurt? Well, it's the fact that a tiny little hard plastic block just sank into my skin. These are all properties. Every one of these things is a property. Okay, the property of the Lego. The Lego is large. The Lego is small. The Lego is hard. The Lego has corners. My skin is soft. All of these properties that I've identified, I can now take that and use it in the future. I should probably keep the bricks on the table. But how do I do this logic thing I was talking about? Well, really, logic is just it's any kind of process. Drivers on the road have to follow a process. Mathematics is very logical. It's a self-contained logic system. Even business operations, there are formal processes for how things have to be done. Communication, how do I express something to someone? They're all just rules. Okay, but how does this apply to me? Okay, back to scaffolding. The action of logic is making progressive steps toward a conclusion, correctly or accurately following rules or properties that have been given or discovered to get there. So I experience a thing. I stepped on that Lego. I experience another thing that is similar to the first thing, and I identify those properties which are similar. I stepped on a pen. I now know how to interact with the things that have those properties. Do not step on hard plastic objects. And I can propose that in the future, if I put even another thing on the ground that I haven't stepped on before, but it's hard and it's plastic and it has a corner, I'm probably going to get hurt. I'm learning again. These are Piaget steps again. What I'm actually doing is applying logic, because learning is just logic. Knowledge itself is gained by experiencing everything around us. It's things we hear, it's things we see, it's things that are said to us, it's things we discover in experimentation, it's things we taste. Everything that we experience gives us properties that we then can use to broaden our understanding and increase our abstract knowledge bank. In this case, thus the teacher became not a transmitter of knowledge, but a guide to the child's own discovery of the world. That's all learning is. It's exploring the world around us and identifying these properties and taking those properties and expanding that knowledge. Now our abstract knowledge is even larger. Again, logic is nothing more than following rules, and these rules are specific to circumstances. So the logic of the road is different than the logic of stepping on a Lego block. Okay, but we called this the methodology of science. So let's bring this back to the topic. So the methodology of science is the sciencing bit. That's actually what the science part is. It's not the experimentation, that's a part of the science. It's the entire idea of science. And science is really just five steps. We experience something or a lack of something. We identify the properties of that something. We classify that property. So now we're organizing, we're categorizing. We're saying property A belongs in this category and that category, and property B belongs in that category, but another category as well. We run it through our knowledge bank and we propose ideas. So now we're comparing it to other pieces of information we have and other properties. And of course, the fun part is that we actually get to do these ideas. Okay, hold on. That should sound familiar. Because science is learning. It's each one of our steps plus the fun part at the end. That's science. Science itself is just really the process of learning, but we formalize it. And since science is learning, and learning is logic, we got our little double equal signs there. That means logically comparative or equal. Science is really just logic. Logic is happening anytime anyone does anything. You wake up in the morning, you have a thought. There was a logic, a followed process that got you to that thought. You drove down the street. There's a process that you followed. Logic systems can be simple, they can be very complex, and they're unique to circumstances. In science, we have agreed upon logic processes, and we'll get to that in a second. In science particularly, there are too many variables. So we're able to actually constrict things. So we cut out variables we don't need, and we talk about only specifically what we want to. And then we have mathematics and philosophy, which are self-contained logic systems. For example, there's formalism and logicism. Formalism is the binary logic system that's used in mathematics. It's why we're able to say, if not this, then this. Logicism is the philosophical logic, the primary philosophical logic system. And these are necessary because they provide the rules for communication. But logic is everywhere. We've got logic in psychology. We've got logic in business. Logic's in family life, music, industry. It's everywhere. Whether it's I have a beginning and a desired outcome, so I pick that process, or it's I don't know where I'm going, but I have some information that can kind of inform me as I go along. Either way, you're following a logic process. Using it is really just going backward. So we're going to reverse the flow. Understanding that we use logic to interact with our world means that we can refine it. We can identify it, slow it down, clean it up, and follow it step by step. We can follow each progressive step that got us to the next step. This helps us to make sure that we aren't missing any sheep. Did we count them all? Is there something missing? Because if something's missing, we're not going to have all the pictures in the puzzle. We're not going to really understand what it is we're looking at. And worse, we're not going to be able to explain it as sufficient. And if we don't know all the pieces to the puzzle, we can't give those pieces to somebody else so that they can see the final product either. So we're going to walk backward. If learning is climbing up the mountain, communicating is walking right back down. So we're going to go back down the scaffold at this point. We start with our hypothesis. We understand the rules that got us to that hypothesis. We understand the properties that develop those rules. And we find the trigger in the beginning. Notice it's really just the reverse of Piaget's development. Learning is the reverse of communicating. Communicating is walking through that flow. So we're going to start with an example. This is a good example, mostly because I wrote this presentation while I was making lunch for my children. So why did you make lunch? Well, I made lunch. I was hungry. The entire conversation. What's missing is this entire segment in the center where I'm making inferences. Now, it's pretty clear what those inferred steps are, but only because it's a simple case. We dropped identifying similar situations and interacting with properties. For those familiar with logic systems, this is really sort of a syllogism. We're taking one step and connecting it to the next step until we get to our final argument or conclusion. But I don't need those because it's pretty obvious that that was what was in the center. But what if it's not so obvious? Our next example, why did you paint the accent wall teal? Well, I chose teal paint for the accent wall because I like teal. Not very informative. I mean, yeah, it gives information. And from my standpoint as the speaker, it makes sense. I like teal. It makes sense. But the recipient, the person who asked the question, doesn't really understand the process, doesn't understand how that applies. So let's walk through here. Really, my logic for this, I chose the teal for the accent wall. The accent wall needed to be painted. The accent wall provides feeling to the room. A touch of ocean colors can encourage calm feelings. And we want calm feeling in the dining room. So my thought process went this way. I experienced that we wanted calm feeling in the dining room. I happen to know the property that calm feelings are encouraged by ocean colors because I experienced that. The accent wall of that room can provide feelings to the room. So the accent wall needs to be painted. So I came to my conclusion. But when I'm explaining that to someone, to my spouse, I'm going to say the conclusion. Then I'm going to say the accent wall needs to be painted because the accent wall provides feeling to the room. A touch of ocean colors can encourage that, and we wanted feeling in the dining room. And by walking my partner through that process backward, they actually get to follow with me to the very beginning step where we originally were, whether they were there or not. So our thought process goes up, but our explanation process goes back down. Being able to reverse our logic process and understand it means that we can clarify not just our communication to other people and identify maybe where we're missing parts, but also within ourselves. It gives us time to slow down and evaluate. Again, are we missing pieces? Are we missing data points? Have we really understood those data points and those properties? Have we applied them in the appropriate manner? Are they appropriate to this situation? Why might they not be appropriate to this situation? So discourse and self-reflection can be refined. Beneficially, if everything in our world is really an internal logic process, if our phenomenology is a logic process, that means that everything we do can be analyzed and reflected upon, and thus clarified. And in that way, we begin to understand maybe some properties we didn't know we were applying. The term the eye seeing the eye. So there may be lenses and properties that we apply to things that we don't even realize that we apply, that other people aren't applying. But if we take the time to slow down and evaluate our process, we can begin to identify where those things are and help other people understand our own frame of reference. So yeah, this sounds really simple. I've pretty much taken 4 major areas of study into a tiny little segment and spoken just a little bit about them and made it sound easy. It is very complicated, and it can get really, really complicated. The more things you add, more properties there are, and the more subjectivity there is. But ultimately, we're just sitting down and reviewing our process. We're sitting down and reviewing each step of the way. So this will be up in the JMP community. And you're welcome. I encourage all of you to read on these things: phenomenology, epistemology, Jean Piaget, developmental psychology, and of course my favorite, logic. That is all I have. So if we have any time, Julian, I hand it to you, sir.
Thank you so much, Fiona. I'll just remind everyone to interact with Fiona in the user community, community.jmp.com/jumponair. We'll have all the material she referenced. And yeah, if you have any questions, definitely reach out to her there. I'm so happy we had a speaker on Jump On Air who talked about epistemology and phenomenology, 2 of my favorite things as well. In our next segment, we have Artie Meidel back here to do another mindful moment for us.
Hello, everyone. My name is Arti. Welcome to the Mindful Moment. This is your opportunity to apply mindfulness to a little bit of movement and breath. And just as a reminder, mindfulness is paying attention to the present moment on purpose and without judgment. So we'll do that with a little bit of movement followed by some breath. And hopefully this will help you to have a little bit of relaxation and a break away from the computer. So I'm going to push my chair back a little bit so you'll be able to see me. And just come to the front of your chair. If you're seated, if you're standing, that's completely fine. You can do all of these same things while standing if you're at a standing desk. So let's just begin by rubbing our hands together, warming up our hands. And then just shake out your hands. And then maybe close them into fists and open the fingers wide. And then just rest your hands back down on your lap, and we're going to take a few deep breaths. So inhaling deeply through the nose. Open the mouth and exhale slowly. Again, inhaling through the nose. Open the mouth and exhale. Last time like this, inhaling through the nose. Open the mouth and exhale slowly. Now begin breathing through the nose alone. So inhaling and exhaling through the nose. So placing your hands to the sides of your chair or to the sides of your body, begin rotating in your seat. It's really a rotation of the hips. So you can make this a big circle or a little circle. It's up to you. So the torso is staying pretty still, and you're just loosening the lower back, loosening the hips, and begin breathing, inhaling and exhaling through the nose. Just breathing normally. And then let's reverse direction. Making the circles with the hips, with the seat, a big circle or a little circle, up to you. And keep breathing. Okay, now come to sit up tall, come to stillness, and raise one arm, and then the other arm is pointing down. So one hand is up in the air, the other hand is down. And inhale here, and exhale, switch arms. The other arm rises, the other hand reaches down. So we're just going to do this seesawing of the arms with the breath. So really think about or focus on connecting the breath and the movement. So inhale and exhale, inhale and exhale. Just seesawing the arms. Inhale and exhale, inhale and exhale, inhale, exhale, inhale and exhale. And then the next time you come to the inhale, pause. One arm is raised, the other arm is down. It doesn't matter which one. Inhale here, and then exhale, bend to the side. So feel for a side bend. Feel for the stretch on the side of the body from the waist up to the shoulder, maybe even through the arm. Inhale back up, and then exhale, we'll side bend to the other side. Inhale here. Feel for that stretch again. Inhale again, then come back up. Let's do the other side. Just really stretching the side body here, inhaling and exhaling, switching arms here. And then come back up, lift the arms up overhead. Hold on to opposite elbows here, and just lightly with your fingertips, framing out your head. And inhale here, and then exhale, a side bend to one side. And notice the stretch this time. Maybe if you're feeling it in a different place, perhaps in the shoulder area, maybe underarm. Inhale back up. Let's lean to the other side. Exhale. Again, notice the stretch. Find where you feel the sensation. Inhale back up. Once more to each side. Exhale, lean. Inhale up and exhale, side bend. Now inhale back up, release the arms, roll the shoulders. Sit up tall again. Feel your feet on the ground, whether you're standing or seated. Close the eyes, and we'll just begin some deep breathing with a 5-count breath. So how it'll work is inhaling for 5, holding at the top for 2, exhaling for 5, and then holding the breath out at the bottom for 2. So let's begin. Inhaling for 5, 4, 3, 2, 1. Hold at the top for 1, 2, and then exhale for 5, 4, 3, 2, 1. Hold the breath out at the bottom for 1, 2. Inhaling 5, 4, 3, 2, 1. Hold for 1, 2. Exhale 5, 4, 3, 2, 1. Hold for 1, 2. One more round like this. Inhale for 5, 4, 3, 2, 1. Hold 1, 2. Exhale for 5, 4, 3, 2, 1. Hold out for 2, 1, 2. Now begin to breathe normally, keeping the eyes closed for one more moment. Noticing how you feel. And giving thanks to yourself for taking a moment to be mindful. You can open your eyes when you're ready. Thanks so much for joining me today.
Thank you so much, RT. In our next section, our next segment, we have Jump in Action again for which, what, and when with reliability analysis with Jerry Fish.
Hi all, my name is Jerry Fish. I'm coming to you from the town of Martinsville in the great Hoosier state of Indiana today. That's where my home is. So let me share my screen. And today we want to talk about JMP's reliability tools. Now, JMP has a large amount of reliability tools, and I've got some of them shown here. It's found under the Analyze, Reliability, and Survival menu. And you can see that there are 13 or 14 of these different platforms within the Reliability and Survival group. These are all very interesting. I've got 15 minutes to talk about them though, and there are even some subtopics under some of these. So clearly I can't go into a lot of depth today. So this is a very high level view. It's not going to be a click here, then click there kind of a thing. I'm just going to try to get you oriented with some of these tools and what reliability analysis is all about. In reliability, we're generally trying to make estimates on when a particular product might fail. So we're making a lot of widgets, and we want to know when those widgets on average are going to fail, or when 10% of them might fail. Those kind of questions that we're trying to answer. Some of these reliability tools can also be applied to, in the medical field, to patient survival rates. Hopefully we'll have a little time to get to that a little later on. The measurements involve how long something is operating under its operating conditions. So a motor, you might measure the response of a motor, whether it fails or not, based on the time it's been operating or the number of rotations of the crankshaft or something like that. And we're counting that time or those cycles until the product fails. Now, as we're testing product though, we may have some of the engines, for example, that don't fail before a certain time, before the end of our test. That's all that we can afford to test. Those particular kinds of observations are called censored observations, and they are good data. It means that those particular units that you've tested have survived that long and obviously go longer. So we include those in our analysis by marking those as censored data. We may also record the cause of the failure. So, and we'll get into that in a little bit with competing causes, so that we can analyze the behavior of the failures due to cause A versus cause B. JMP really has what I think of as three different kinds of reliability analysis. There are non-repairable systems. These are the ones that maybe it might be a toaster, where when the toaster breaks, it's done. We're going to throw it away. We're not going to take the time to repair that toaster. Repairable systems, on the other hand, are something that often they're bigger, more expensive units, maybe like your car. That's something that you do want to repair to keep it on the road. You don't just throw it away when it fails. So there we're interested in the repair rates. How often do we have to repair things? What are the tools or the parts that we need to have on hand to repair those things when it happens? And then survival tools, again, applies to patients. Here we can actually get into modeling, looking at some of the covariates and how they affect the reliability of the output. So let's go through a few of these. Like I said, I wish I had more time to give you more information on these. Up here at the top, you'll see my name and my email address. If you want to get more information about these, I'd be happy to provide it for you. Let's take a quick look at life distribution. Here we've got a data set of a number of electric motors. Each row represents a motor that was tested We measured the number of cycles until it failed. So motor 1 here only ran for 2 kilocycles, and it failed. So the sensor code, it's not censored, so we give that a 0. And the cause was due to a surge. We observed that. And so forth down the list. We've got 30 motors in all. If I just run the life distribution script, we get a couple of different plots here. This plot on the left just kind of summarizes all of our raw data. And if I come down here, this is really where the output lies. This is, if I put in a certain number of kilocycles, let's say 100 kilocycles, I want to be able to predict what percentage of my motors or what fraction of my motors is going to fail at 100 kilocycles. So if I put in 100, I see that I can expect 35, based on the data, I can expect 36% of the data within these confidence bounds to have failed at 100 kilocycles. Conversely, if I want to know when do 10% of my motors fail, I can use the quantile profiler. So 10% of my product would fail at 21 kilocycles worth of cycling on the units. So that's how life distribution works. Now, if you were paying attention, you notice that we had the cause column, and I did not say anything about the cause. We can also bring data in for the cause, and JMP will separate out the different curves that make up the overall product reliability. Here we see that surge is the red curve right here, and wear out is the blue curve. Surge happens if there's a voltage surge or a current surge in the incoming power line, and it can happen really any time. It's not a function of the design of the motor. And so we see that it dominates the reliability, the overall aggregate reliability in the early stages of life. Later on, we get motor wear out, which may be, say, a bearing failure. That takes off later in life. And so we can see the two of these causes and understand a little bit about how they contribute to the overall reliability and know which one to attack in our design. Now, sometimes you're going to have a situation where you just can't test the product out to its full life. Let's say fluorescent light bulbs. They may last for years. They're designed to last for years. Well, you can't really test a light bulb to years. If you did, you would be behind the scene or behind the times when it comes to announcing your product. So we need to accelerate that testing somehow. And there are a number of ways that you can do that. People use running a product at higher temperatures, subjecting it to vibrations, using excessive loads, excessive force on your product. A lot of different ways to accelerate the failure. The key is that when you put these accelerators into play, you don't induce a separate kind of failure. You always want to keep your accelerators so that it's giving you the same kind of failure that you see at your normal operating conditions. Let's take a quick look at that. Here we have some data where we've run at different temperatures, 10 degrees C, 40 degrees C, 60 and 80 degrees C. We've got a number of products that we tested at those different temperatures. The ones at 10 degrees C, we had 30 products, and they all were censored. They all made it to the 5,000 hours. At 40 degrees C, we had 90 units that made it to 5,000 hours, but we had all of these others that failed along the way. So that's what we're trying to understand is how does temperature affect the failure rate, and can we then project back to normal operating conditions where we didn't have any failures to find out what the failure rate would be. So here's fit life by X. This top chart again lets us look at the individual data. We've got temperature at the bottom axis. We've got hours here on the horizontal axis. And we can see that at 10 hours, we didn't have any failures, and we get more and more failures over time. JMP then builds a model that fits curves to each of those temperature conditions, and then gives us a profile in the end that says, if I want to operate at 10 degrees, what is my failure rate at maybe 10,000 hours? And it says that if I ran to 10,000 hours at 10 degrees, I would estimate a failure rate of 0.007%. So that's the idea with accelerated life testing. Degradation testing has to do with when something doesn't actually fail, but it degrades over time. So here's an example of a laser that we're measuring individual units. So here's unit 1. We take measurements of the current input, the electrical current input to that particular unit over time. So we don't really have the laser failing. It's just drawing more and more and more current as we go along. We'll say this is milliamps of current. So here's the degradation chart. And the degradation chart shows us for each one of those products or each one of those units where we took many, many, many measurements, these are the trend lines for each of those units, and we can look across this graph now and figure out, say at 5,000 hours, what percentage of our product would have failed in terms of exceeding 10 milliamps of current. What percentage of our product would have failed at 5,000 hours? So that's called degradation analysis. Kind of a special subset of degradation would be in the medical field or in the pharmaceutical field, drug stability studies. Here we've got drugs. Here is batch number 1 of a particular drug, and we're interested in this concentration. The concentration degrades over time, and we're interested in limiting that. We want to know, in order to put a claim on our bottle, what happens, how long can we guarantee that it's going to last and maintain its efficacy above a level of 99, a concentration of 99. For that, you can go into the stability platform, and this shows each one of those batches is a different color in the lines. This is time on the horizontal axis and concentration on the vertical, with our spec of 99 shown here. We see that this green batch is the worst batch in terms of when it gets to this 99 level, concentration level of our cutoff. And we're estimating when does the lower 95% confidence level get to this level of 99. And that occurs here at 4.5 days, or whatever this time unit is. So we can estimate that that's probably what we would want to put on our packaging to say that we think that this product will maintain concentration of 99 or above for at least 4.5 days. Destructive degradation, I'll skip that. It's just if we have a product like an adhesive bond and we're measuring the degradation of the strength of that bond over time, you have to actually break the adhesive bond in order to make a measurement. So that's called destructive degradation. There's a platform for that. Then reliability block diagram is a JMP Pro feature. I've got it shown here in red. So if you have standard JMP, you won't have this feature available to you. If we have done our analysis on individual components with all the tools I've described so far, we can then in JMP Pro build what's called a reliability block diagram. Here's an example of a braking system for a car. The car has a master cylinder, it's got cylinders on each wheel or calipers on each wheel, and it's got pads and shoes on each wheel. It's also got an emergency brake system. We do our reliability analysis on each one of these in order to add everything together to get to the end result. And that end result is the distribution over here on the right. So again, we can estimate how long, what probability of failure do we have at, say, 10,000 hours, we would expect 64, 65% of these to have failed at that time. Okay, my time is rapidly passing. Let me make a few more comments and then I'll give it back to Julian. Recurrence analysis has to do with when we're looking at failures of a given product, a turbine engine, for instance, and you have to repair those failures. How often do those failures come along? What do those failures cost you over the life of the machine? Reliability growth then says, let's say I'm not happy with that failure rate. What can I do to improve it? How do I take into account changes that I've made? Have I actually made improvements to the reliability or not? So that's reliability growth. Similar to the reliability block diagrams, there's a platform in JMP Pro that allows us to look at repairable systems and build those systems together to look at what parts do I need to have on hand to repair my systems. And then reliability forecast is a tool that we use to estimate the cost of warranty work. If you have product that's in the field and you're getting returns on that, how do we estimate that rate of return? And given the length of the warranty period, how do we handle those kind of claims, and what can we expect in terms of total cost coming up in the future? Well, I have run out of time. Survival tools I didn't even get to. Again, those have to do with people, survival rates, say, due to different kinds of cancers and so forth. If you have interest in those, I'd be glad to talk to you further about it. But I'm out of time, and I don't want to take time away from Pete Hirsch and Mary Lovelace. So I am going to kick it back over to Julian at this point. Thank you for your time.
Thank you so much, Jerry. You packed a lot in there. We really need to give you a longer segment. We really appreciate it. And yeah, people have questions. community.jump.com/jumponair. We'll have Jerry's segment up there, and I'm sure he'd be willing to engage with more questions. Yeah, thank you so much, Jerry. As Jerry mentioned, in our next segment, we have Pete and Mary back to act out real-life situations where a jump tip is the answer.
Hey, Pete. Once again, this is Pete and Mary's tip and trick of the day. So I got my hat out, my trusty hat, my Boston Strong, and let me sort of go in here. Oh, look, we got a tip from Hyde Miller.
Oh, hi, great.
Yeah. So Hyde's tip is shortcuts for creating report windows and more. And Hyde is part of the Global Technical Enablement Team. So he covers the globe.
The globe.
The globe. So anyhow, so Pete, do you want to sort of share with the group what Hyde is referring to with creating report windows and more?
It just so happens I have a very messy JMP desktop right now. So you can see if I open my home window here, I got a bunch of stuff open.
You do.
So I think one of the things Hyde wanted to highlight is if I have a report open like this, there's little buttons down here. So I can click on the home, which takes me back to the home window. He also likes this, where I can click on this, and it takes me to the data table. And you see all those open reports that are associated with that data table.
Hey, Pete,
yeah.
Can you go back and bring up one of those reports?
Sure can. Let's.
You know why? Because did I see that if you go to the data table window on the bottom, there's a shortcut key, Control-Alt-D. Go to the data table.
Yes.
That's Control-Alt, so I can even use the shortcut key.
Yes, Control-Alt-D. Yes, that's
okay.
Good one. Yeah, so you can find that. One other thing in here is this little checkbox. So I can check this box and check a couple boxes and combine them, or I can just go to this drop-down menu and combine windows. And so you can see all of my windows I have open, but why don't I just pick a few here and hit OK. And what JMP does is it makes a dashboard. Since I have limited resolution here, I'm going to just drag these together. And now you can see I have a dashboard with all three.
Oh, and you know I love tabs. I love tabbed output, and I didn't even have to write any code.
It's amazing. Yeah, I know. I know.
Right.
Yes.
And it creates it for me. Awesome. So we learned about on the bottom right, there's a little home window, and then how to bring the data table front and present or use a shortcut key, and then the button to arrange the output.
Oh, I had one more thing from Hyde. You notice?
Oh, you did?
Yeah, you notice how much junk I have open here in JMP. So I could go through and close these one by one, but what a pain. I can also select a bunch of these, right-click, and hit close, and I can say no. Or I can select a single data table and say close all but this. And then I just have that one data table.
That's awesome, because a lot of times I'll go through and I have all these subsets and different things I'm doing. The next thing you know, I look and I go, oh my God, I got to step through it. So close all but this is awesome.
Yes.
Well, thank you, Hyde, and thank you, Pete, for enlightening me.
Yes, thank you. And this has been another JMP On Air tip of the day.
Outstanding. Thank you so much, Pete and Mary. We've really had a good time with you on the show today. After today's show, make sure you submit your abstracts for JMP Discovery Online. Deadline is Friday, so the link to remember is discovery.jmp. Make sure you visit our community page, community.jmp.com/JMPOnAir. You can interact with all of our speakers and get all the data and anything they mentioned during their segments at community.jmp.com/JMPOnAir. Follow us on all our social media channels. Check out your programming guide. We have a great show for you Friday that you'll want to share with your colleagues. So the link to share is jmp.com/JOA. But until then, we hope you stay safe. We hope you stay healthy. We hope you stay close, even as you're keeping your distance. Happy Wednesday, everyone. Take care.